hear you?
Yes, thank you.
And we can hear your screen, so go ahead.
Okay, thank you. Yeah, hello everybody. My name is Jiang Junwei from Sichuan University, and this presentation is about our paper, second-order explicit pressure projection method for Eulerian fluid simulation. Our scheme is based on the advection projection framework from the perspective of Euler. So we will first make a review. The incompressible and inviscid NX equations can be written in the following forms. The first is the momentum conservation equation, and the second is the mass conservation equation. And using the method of operator separation, the advection projection framework divides its evolution with time into two main steps. Namely, the advection for solving the advection term and the projection for solving the pressure gradient term, and ensuring the conservation of mass. This has produced an extremely stable fluid solver and has been widely used in the field of graphics. However, this scheme will cause great fluid energy loss, which is manifested in the rapid loss of rotational motion or vorticity dissipation. We can take an example to observe this phenomenon. This scene is called Taylor vortex. Two vortices are placed close to each other, close to each other beyond a certain distance, and two vortices will separate from each other over time, as shown in the reference on the right. Yeah, as you can see, the traditional advection projection scheme cannot achieve this goal because of its high vorticity dissipation. Next, we will analyze the reasons. There is the velocity field of the previous scene, from which we intercept some segments for analysis. We select any grid point and assume that it's at the spatial position x. When entering a time step, it has a horizontal right initial velocity. A typical advection operation will calculate its characteristic line according to the current velocity field, or trace back to find the blue dot in the figure. And its position is obtained by using a backtracking function. Then take the velocity of the blue dot as a temporary velocity of the next moment of the red dot. Next is the projection step. The velocity field after advection is divergent, and the mass is not conserved. The projection step essentially performs a Helmholtz decomposition to obtain a divergent part and a non-divergent part, which are represented by green and red arrows, respectively, in the figure. Then discard the divergent part to obtain a non-divergent velocity field. In fact, the projection operation actually does two things. One is to calculate the pressure in the current state, and the other is to apply the pressure gradient to the velocity field. The projection operation only at the end of the time step is mathematically a backward Euler method for the pressure gradient term. So obviously, this has only a first order time accuracy, and the loss of accuracy is represented by the excessive loss of fluid energy. The solution is to adopt the second order time integration format. One of the most common choices is the midpoint method. That is, the pressure gradient at the time n+1 in the formula is replaced by the pressure gradient at time n+half. For schematic diagrams, is to find the pressure gradient at the midpoint of the characteristic line or trajectory line, and use it to estimate the pressure gradient over the whole time step. Now we need the pressure gradient at any grid point after a half a delta t. Because we use the explicit scheme, this value uses the exp subscript. Incidentally, the reflection solver can be understood as the implicit form of this scheme. And returning to our paper, in order to achieve the above goal, and we assume that we have the pressure gradient at the beginning of the current time step, we only need to get the local rate of change of the pressure gradient with time at any grid point. So we assume that the time rate of change of the pressure gradient of a fluid particle located at a certain point in space at a certain time is expressed by a function, which x represents the spatial position. We expand it from the perspective of Euler to get this, and then move the term to get this. The first term is the advection term, which is also the object of our fitting. In other words, we perform an advection operation on the initial pressure gradient field to obtain the approximation of the pressure gradient field at the intermediate time we want, and apply it to the temporary velocity field, and then perform projection at the end to ensure boundary conditions and mass conservation. Again, the implicit scheme can be fitted together with the second term, so the effect is better than our explicit scheme under the same parameter settings. But our experiments verify that we will not lose too much accuracy, but can save twice or even more computational overhead. Here I posted the pseudocode of our algorithm, in which the original operation of the advection projection framework is framed by a blue rectangle. The second order explicit pressure gradient scheme we just described is framed by a red rectangle. And the part selected by the green rectangle is our next topic. When deriving the pressure gradient at the midpoint, we made an assumption that we have the initial value at the beginning of the time step. However, the advection projection scheme does not save pressure, so the situation may be worse for the following two reasons. Our change to the original projection framework makes the potential field obtained by the Helmholtz-Hodge decomposition only a correction of pressure, not a complete pressure. And in our method, the accuracy of pressure will affect the accuracy of velocity, so we need more accurate pressure. So we introduced the pressure incremental correction scheme. That is, the pressure is explicitly calculated and saved as a fluid variable, and the advection occurs as the fluid moves or time advances, which corresponds to the fourth line in the pseudocode. And at the end of the projection step of each time step, the potential field obtained is corrected to the pressure field after advection to obtain the initial pressure field of the next time step, which corresponds to the 7th line in the pseudocode. So the above are all the main steps of our scheme. For more details, please check the paper. So now let's take a look at the results. The first, the computational cost. Theoretically, the computational cost of our scheme is almost the same as that of the advection projection scheme, and it's twice as fast as that of the reflection solver. But it showed unexpected performance improvements. We can see that in most scenes, our scheme is 10% to 20% faster than the traditional scheme. But in the 3D smoke plumes scene, which is a high resolution scene, our scheme is even 3 times faster than the original advection projection framework. This is because our method has applied the nearly correct pressure gradient to the velocity field before performing the most time-consuming pressure projection, resulting in the input velocity field of Helmholtz-Horch decomposition being almost non-divergence. Therefore, the conjugate gradient solver only needs a few iterations to meet the convergence requirements. And at the same time, this is also the reason why the computational cost of the reflection solver and the second-order reflection solver in this scene is not twice as high as that of the traditional solver. Then accuracy. Theoretically, our scheme has second-order time accuracy. We have carried out a numerical experiment and a large number of effect experiments to verify it. In the numerical experiment, we choose the Taylor-Green vortex scenes. Its initial velocity field is shown in the figure, and its analytical solution is given by this formula. Similar to many other papers, we ran it to 1 second and computed the RMS error in velocity with respect to the analytical solution. The picture on the right shows the double log plot of this error as a function of time. So we can see that our scheme and other second-order schemes have achieved the expected results. And for effect experiments, we made a video to show them. and summary. By analyzing the defects of the original advection projection scheme, we modify the calculation process of the pressure term in the NS equation and obtain a second-order time accurate fluid simulation scheme, which also reduces the computational overhead to a certain extent. However, our approach also has some limitations. First, even if we consider the influence of pressure gradient on the fluid motion with second-order time accuracy, the error of advection operation still exists. We suggest using a high-order advection algorithm to meet the overall accuracy requirements of the solver. And second, the introduction of explicit pressure makes us have to consider additional pressure boundary conditions. In this paper, we simply specify it without in-depth research. We think it may be one of the potential research field. And that's all. Thank you.
All right, thanks, Jimei. Questions? I'll start off with a quick question. So there's a million, second order, higher order schemes, out there in the literature, including for just, purely Eulerian fluid sims. In your paper, how did you think about choosing which methods to compare against, and what would be your argument, if you have one, for why a practitioner should pick your method over maybe another, second order Eulerian fluid scheme that's out there?
I'm sorry. So you want to ask our advantages to other second order schemes?
Yeah, advantages, and also just how you chose sort of which other methods out there to compare against.
Just like the reflection solver, the projection step mainly focus on mass conservation and the boundary conditions, but most of them have twice pressure steps in one time step. Is too expensive for computing, and we using explicit steps to replace it and maintain the last projection steps to maintain the mass conservation and to reduce the computational cost. So I think the advantage of us is we are more faster. I'm sorry.
Great, thank you. Other questions? All right,
Thank you for the talk. I am not working on fluid association. Probably my question at the point, but I recall that from this year in SCA, there was a paper called COVID for the fluids, and they were trying to solve projection set on fluid simulation in like as well. And I would like to know if there is any relation between your work and their work, or if it is a completely something different. If you
I'm sorry. Maybe there's some echo, and I can't hear it clearly. So could you explain it again? I'm sorry.
So I think the question was: is there any relation between your work and a SIGGRAPH paper this year that was covector fluids? If you've heard of that paper.
I heard the paper of Zender published in SIGGRAPH in 2019, the reflection solver. Is it? I'm sorry.
I think the question's about a paper from this year.
Yeah, I hear. Maybe I know this paper. When I read this paper, I saw the preprint version of that paper. But I think the two paper have some difference. My start point is to using a explicit method to improve the reflection solver. I think that paper using the concept of Jacobi. I'm sorry, I didn't know detail about that paper.
Yeah, thank you. That's no.
All right, sounds good. I think we'll go ahead and wrap up the session there. So thanks again to all the speakers this afternoon. Great talk.